thank you very much. It's a great pleasure to have you all here. I'm Leonardo Cavenaghi, one of the organizers. This first talk is being simultaneously shared also with ICMS in Sofia, Bulgaria. And it's a great pleasure and an honor to start with Professor Phillip Griffiths, who is like one of the fathers of modern algebraic geometry, complex geometry, such that the same way as King Midas, everything that he put his hands on become gold, and not only mathematically, but also in the development of like mathematical sciences through the world. For instance, through his substantial contribution to the development of IMSA and ICMS, also in Bulgaria, as twins institute to the progress of mathematics. So once more, it's great pleasure to introduce you Professor Phillip Griffiths. He's going to speak to us about normal functions and their variables. Very various. Thank you, Mr. Professor.
Thank you, and thank you to the organizers for putting together what looks like a great conference. A lot of what's like very interesting topics, talks, and I'm looking forward to it. The talk I will give will be a sort of general talk on a classical subject in algebraic geometry. Algebraic geometry in the beginning was always interested in algebraic varieties, and in particular in the subvarieties that lie in an algebraic variety. For example, of an algebraic curve, a very classical question was, given a set of points, when is it the divisor of a meromorphic or rational function on the curve? That is a function whose zeros and poles are the given configuration of points with multiplicities. When you come up to algebraic surfaces, for example, the classic example of a conic, which has two rollings, the cubic surface, which has a smooth one, has 27 distinct lines, and so on. I'm going to be particularly interested in the higher dimensional case, specifically of curves lying on three-dimensional algebraic varieties. But that's just part of the story of general interest of the configuration and position of subvarieties of an algebraic variety. So here this just represents sort of the classical criteria that a set of points be the zeros and poles of a meromorphic function, writing the zero cycle as the boundary of a one chain and integrating regular differentials, holomorphic differentials on paths connecting it. You get a point in so-called Chow variety, and the necessary and sufficient condition to be the divisor of a function is that should be zero. So normal functions are going to be an extension of this idea to higher dimensions and where the objects depend on parameters. So the emphasis will be on, so the normal function will be called mu, and the emphasis will be on what happens to a normal function when you vary the geometric configuration with parameters. Frequently, it's difficult to say something explicit when you don't allow parameters for reasons I'll explain, and normal functions are a way of getting at this phenomenon. So the normal function is a sort of transcendental type object, like the oval Jacobi map on the first slide was an integral of an algebraic differential form on an algebraic curve. Those quantities you get by integrating are transcendental functions, not algebraic. So getting at them requires a new way of thinking about things. And one way of doing it is to see how they vary, how the integrals vary when the points vary on the curve, or more generally, when the curve and the points vary, how does the measure of the geometry of the curve, pick points on the curve, how does that vary? So that's what a normal function will be in general, and it will have an infinitesimal invariant, and that's an algebraic object. So it's a way of getting at this transcendental thing by looking at how its derivative, if you like, is. The infinitesimal invariant is sort of the intrinsic part of what you get just by differentiating in naive calculus sense. So both the normal function and its infinitesimal invariant will have continuous parts, and when the configuration becomes singular, there will arise singularities of both the normal function and of its infinitesimal invariant. So again, going back classically, one way of studying configuration of subvarieties of an algebraic variety that may be difficult to get at directly is to degenerate to something singular and just see what happens in the limit and how much can you infer for what happens in the interior or what happens in the limit. It would turn out that the singularity of the normal function has a Q structure. It's defined over Q. It's like homology of an algebraic variety. It's going to be monodromy for the case of a normal function. The singularity, on the other hand, has a continuous structure, and it basically is a Hodge type structure. And the fundamental result that I'll try to describe some of identifies the singularities. So even though the normal function is transcendental, in the limit, its singularities are the same as the singularities of an algebraic geometric object. And that can, I think, be one way of getting at the geometric behavior of the algebraic cycles that you're interested in. So a few of the application of classical ones of normal functions. First is the old result of Clemens and Poisson. And here again in dimension 3, looking at curves, so that's codimension 2 on a 3-dimensional variety, the behavior is extremely different from that of points on an algebraic curve or even curves on an algebraic surface. So if you look at the algebraic cycles and look at algebraic equivalents, you can move one to the other through an algebraic family. Okay. Then quotient out the group of algebraic cycles by this type of equivalence. The original equivalence in algebraic geometry was rational equivalence. That arose from the fact that the zeros and poles of a meromorphic function are rationally equivalent. You just move the poles to the zeros by parameterized by the projective line. The result of Clemens-Poisson is that on a generic number of, I would say almost most Calabi-Yau threefold, this quotient group is infinite, is an infinite discrete group. So it's quite a different type of geometric object than one has classically. Another type of thing are the results of Green, Poisson, and others on hypersurfaces in projective space. And the geometric content of this is that when you're looking at algebraic subvarieties of subvarieties in projective space, hypersurfaces, to get really interesting one, you have that interesting means it's not a complete intersection of a bunch of hypersurfaces with the original one. To get really interesting ones, you have to go to pretty high codimension in the parameter space. So they occur more and more rarely as the degree of the hypersurface goes up. Another particular normal function that's a very beautiful object arises from an algebraic curve of genus 3. So that's just one-dimensional compact complex manifold ring on surface. Its Jacobian variety So that's the thing that the Abel-Jacobi map maps to. It's the abelian variety canonically associated to any smooth algebraic curve. So for genus 3, it's a three-dimensional algebraic variety. It has its own intermediate Jacobian. Higher dimensional varieties have things that are generalizations of the Jacobian of a curve. So we're looking at the three-dimensional Jacobian of a genus 3 curve and taking its Jacobian. And looking at the algebraic curves in the Jacobian of the Jacobian. You can map a curve to its Jacobian just by integrating. You want to know where a point goes, draw a path from a base point to that point and integrate the regular differentials along that path. That's the map of a curve to its Jacobian. The Jacobian is a group, so it has a minus subtraction. Take the curve minus itself, minus its image. So these are curves, one-dimensional algebraic cycles sitting in a high-dimensional algebraic variety, and these things cannot be deformed into one another algebraically, except for a special case of hyperelliptic curves. So there's something subtle going on in the geometry, even of a very classical object, genus 3 curves. Another use of the infinitesimal invariant is you can reconstruct the equations of a smooth cubic threefold from this object. So it has enough information in it, in some cases, to actually capture the variety where you're sitting, so-called Torelli type of phenomenon. Another application of the singularities of the of a normal function and of its infinitesimal invariant. And this is what started really the study of the singularities of these objects, is that you can reformulate the central problem about algebraic cycles, the Hodge conjecture, simply as the existence of a singularity of a normal function that arises from a Hodge class. So given a smooth projective variety, given a Hodge class, that's a class whose Hodge, in the Hodge structure of the cohomology sits in the middle piece. It's this type of cohomology that would arise from an algebraic subvariety. So the question, of course, in the Hodge conjecture is, if you have a cohomology class that satisfies those conditions, is it realized by an algebraic subvariety? Essentially, I'll come back to that. One way of studying the algebraic variety is the classical way that goes back to Picard and Lefschetz, is to take the variety and fiber it into lower dimensional varieties. This is another reason for studying things at very good parameters. So it's a so-called generic pencil. Take your variety in projective space, intersect it with a hyperplane, and just take a generic one-parameter family of hyperplanes. That gives you a fibration of the algebraic variety over the projective line with lower dimensional fibers. Your Hodge class then generates a normal function, and a basic theorem is that any normal function comes from a Hodge class. Second basic result is that the Hodge class is realized by an algebraic cycle if and only if the normal function has singularity. So if you want to produce an algebraic cycle, you take the Hodge class, take its normal function, and show that it has singularities. So far, this has not worked to do much about the Hodge conjecture, but the geometry in it is quite interesting. And again, the use of normal functions, mirror symmetry. I think this is something that many of you know much more about than I do. I should also mention that normal functions have an arithmetic aspect. When everything is defined over a field and you specialize, again, for example, by some kind of degeneration, the normal function becomes, in some cases, computable. And this was used just a few years ago to sort of geometrically explain why zeta of 3 is irrational. It arose in the explicit expression of a normal function that you could prove to be rational for geometric reasons, and lo and behold, the thing that you got was zeta of 3. So the basic map in this is the Abel-Jacobi map. I'm going to stick to varieties of odd dimension and cycles on them of the codimension m. So m equals 1, that's a curve, and points on a curve. M equals 2, that's threefold, and 1 cycles, algebraic curves on a threefold, and so on. There are 2 descriptions of the Abel-Jacobi map. This is the one that you get by integrating a cycle, integrating differentials over a chain whose boundary is the cycle. It's the thing that generalizes the picture in the one-dimensional case. Okay. I'm not going to get into explaining all the notations. They're in the website for the conference. The second is, I think, in the end, going to be a better way of looking at these things. Whenever you have a smooth algebraic variety and a subvariety, you have the Hodge structure on the cohomology of the smooth variety, and you have a mixed Hodge structure on the cohomology of the variety modulo the subvariety, or dually the cohomology of the algebraic variety, take out the open, take out the subvariety. That's a Zariski open. Okay. So the mixed Hodge structures are composed, sort of, in this case, of 2 types of Hodge structure. The Hodge structure arising from the variety itself. So that's like the first cohomology of the algebraic curve, very traditional object, and the Hodge structure arising from the algebraic cycle. In the case of a curve, points on a curve, that's topologically not that interesting, or Hodge theoretically, but in higher dimensions, it becomes more interesting. So on these relative groups, you have mixed Hodge structures. A mixed Hodge structure is an extension of 2 pure Hodge structures, in this case, the cohomology of the ambient space and the cohomology of the subvariety. It's a 2-step extension. 0 goes to A, goes to B, to C, to 0, and there's an extension class. So from general homological algebra type considerations, any such short exact sequence has a well-defined extension class somewhere, and that's equivalent to the classical integrating differential forms over chains description. So the Abel-Jacobi map is defined on the Chow group. That is, if you deform the cycle rationally, you map to 0. The reason is that the thing you're mapping to, the intermediate Jacobian, is a compact complex torus. Any map from a rational from P1 to a compact complex torus is constant. So by mapping under Abel-Jacobi, you're factoring out rational equivalence. So you get a map on Chow group. And I'm just repeating what I said early. Going back to the Calabi-Yau threefolds, one of the early objects was the quintic hypersurface in P4, just degree 5 hypersurface in degree 4, to Calabi-Yau. And what was proved is that so on these, I think many of you know much better than I do how much interest there is the study of rational curves, or in general curves, but rational curves on Calabi-Yaus. Began with the study of lines on the quintic, or more generally, rational curves and arbitrary Calabi-Yaus, but let's just do lines on the quintic. So we have this quintic 3-dimensional hypersurface in P4, and it has a certain finite number of lines, 2,000 some odd. And those lines all give you the same class in homology. by the Lefschetz type theorems. So their difference is zero in homology. That's the boundary of a three-chain. You can integrate differentials over that. That gives you the point in the intermediate Jacobian. And what was shown classically is that generically, this difference of lines is non-zero. So it's detecting, if you like, at least generically on the quintic of the lines. And moreover, the image is discrete, non-finitely generated. And this is the Teresa cycle I mentioned. C is a curve of genus 3, and J of C is the Jacobian variety. That's an abelian variety of dimension 3. And you map the curve to its Jacobian, and that gives you a curve in a higher dimensional variety. You can look at the Aldo Jacobian map on that difference in the group theoretic sense, and the Teresa result was that generically these are not algebraically equivalent. Show how arithmetic gets into the game. You take this genus 3 curve and you degenerate it like this picture. When you do, the curve becomes singular, but the Jacobian variety of the curve remains three-dimensional, smooth, abelian variety. It's just the direct sum of the Jacobian of this curve, that's dimension 2, and this one, that's an elliptic curve, that's dimension 1. So the Hodge structure doesn't see the singularity, but the normal function will see it, and this thing gives an element in this mysterious group, the indecomposable elements in normal K3 of degree 3. So that's just to illustrate how hidden in this what looks like the geometry of normal functions, in the limit, there's a lot of interesting arithmetic too.
Can you say a little bit more about how this K3 arises?
Excuse me?
Can you say a little bit more about why this third K group arises there?
I can give you a reference.
Mm-hmm.
Okay. It's a bit involved because you have to talk about semi-stable reduction, and you have a family, and what happens to the intermediate Jacobian, and that thing then has a structure which, when you dig it out, the arithmetic stuff turns up. Okay. When you're in dimension at least 2, you take a subvariety, the tangent space to the deformation of the subvariety or a cycle in a fixed X. And this is the type of differential that you integrate from intermediate Jacobians. This is the cohomology, and this is the first half of the cohomology in the Hodge decomposition. So you think of a Riemann surface, its first cohomology, the first piece of it is the G-dimensional piece spanned by the holomorphic differentials. And then the quotient is the remaining G-dimensional piece. The first piece is F1, and in this case, M is 1. So this is the differential of the Aldo-Jacobi map. You integrate the differential over the normal vector, that's a tangent space to deforming the cycle, and you get 0 just for simple Hodge or Hodge type considerations. Okay. Essentially, when you integrate, you're integrating something that has too many DZs for the domain of integration that you're on. So you get relations. So the differential doesn't see this much of the Hodge, the filtration. The connected components of the image therefore lie in an abelian subvariety, and the kernel and the image of this Aldo-Jacobi map, there are conjectures that seem far, far in the distance due to Beilinson, Bloch, and others about what the kernel and image will be in general. So coming to normal functions, they're infinitesimal invariant. If your pair varies in a family, then you get a normal function just by taking the oval Jacobi image over each point in the parameter space. And here you're assuming, of course, reasonable conditions that you have a smooth family of smooth varieties. You have an algebraic cycle that intersects properly with the fibers in something that's homologous to zero. So you can talk about its normal function. The classical case are the horizontal curves on elliptic surfaces and the corresponding section of the Jacobian surface. This is just the formal definition. I'm not going to go through all of the notation. As I say, it's in the website. I think these slides are in the website. But it involves the Gauss-Benin connection and what happens to the Hodge filtration under the direct image. So you have a family of algebraic varieties. The cohomology is locally constant, but the Hodge filtration, Hodge decomposition is varying. And the infinitesimal invariant of the normal function is related or uses the properties of how the Hodge filtration varies to define it. The condition that the normal function be constant is equivalent to saying that its lift is just a section of the cohomology bundle. Right, so the local lift is quasi-horizontal. This happens, that's the normal function condition. Geometrically, what you do to lift it, you have to let your variety vary with parameters. So go back and picture your algebraic curve. Let the holomorphic differentials vary with parameters. But that's not enough to give you the calculation of the infinitesimal invariant. Whenever you have a family of points on an algebraic curve, a zero cycle of degree 0, there's a differential of the third kind that has poles plus or minus 1 at these points, depending on the sign. And the differential of the third kind gives you what's called a current, something you can integrate against the infinity form. And that current has to appear in the way that you define the infinitesimal invariant of the normal function. So more formally, the constructions give rise to a Gazoo type complex, and it's the cohomology of that thing that gives the formal definition. The condition that the normal function, the infinitesimal invariant be 0, is that you just lift to a constant section of the cohomology bundle. And so if you have a family varying globally, so you have monodromy frequently, that's enough to say that the normal function is itself actually trivial. As an example of the geometry in the normal function, take a Calabi-Yau threefold, let it vary with parameters. It's well known that the number of moduli is, well, moduli spaces is unobstructed, and there's an isomorphism between the tangent space, the moduli, and in the Hodge decomposition, the second summand. The first summand are just the holomorphic differentials, 3 zero forms. The next summand are the forms of type 2-1, 2 dz's, 1 dz bar. And their cohomology is this proof here. And this is an isomorphism. So the upshot then is that the structure of how the Hodge structure varies when the Calabi-Yau threefold varies gives you a cubic in the third symmetric power of the cotangent space of the parameter space. That's the Yukawa cubic. And the infinitesimal invariant is a point in this group. We take, so whenever you have a polynomial, you have its Jacobian ideal. You take the ideal generated by the partial. And that's the Jacobian ideal of the comma cubic in degree 2. Take its orthogonal complement, and that's where the infinitesimal invariant sits. So it suggests that this infinitesimal invariant interacts with the Yukawa cubic. I'll come back to that later. Another interesting algebraic invariant of this transcendental object is the inhomogeneous Picard-Hughes equation. The Picard-Hughes equation is just the ordinary differential equation satisfied by a one-parameter family of algebraic varieties. If you look at how its periods, when you integrate a holomorphically varying differential against just topological cycles, you get an ODE, Picard-Hughes equation. And for cycles, the Picard-Hughes equation is P of the period is 0. The normal function, just from the way it's constructed, gives you an inhomogeneous Picard-Hughes equation, and I'll briefly discuss that below. There are higher orbital Jacobi maps. This is in response to the question that was asked. And those are the things that appear in the limit when you have a family of algebraic varieties that become singular. The singular one, by semi-stable reduction, will just be a normal crossing variety, and then you get a structure coming out of that geometry. And that's where the higher orbital Jacobi maps turn up in the limit, and those are, they have an arithmetic character. They're like regulator type maps. Okay, for singularities of normal functions, of course, the classical method to study algebraic varieties in general or pairs is to degenerate them. It's one classical method. And you have a parameter space where you take out the singularities will occur along a normal crossing divisor, and you get pictures like this. A GS2 curve sort of degenerated in two ways. One is remains irreducible, and you got a weight filtration on the limiting mixed Hodge structure, whose first associated graded T's is just the homology of the normalization of a singular curve of GS1, elliptic curve. Over here, you have a different type of degeneration, no longer irreducible. The limiting mixed Hodge structure is weight 0 and weight 2, and these are the graded pieces. What about the obel, limit of the obel of the immediate Jacobians? When we assume unipotent monodromy, and in the limit, you get some sort of limiting object, whose first term is a connected complex Lie group, may not be compact, and that's a fibrous space of connected abelian complex Lie groups, and that's where this sort of arithmetic stuff turns up. This filtration, this limit has on it a filtration induced from the weight filtration of the limiting mixed Hodge structure. The associated graded are these higher obel Jacobi maps, and that's where the arithmetic stuff begins to turn up. The quotient is a constructible sheet, which is a local system on the smooth strata of the locus where over which the singularities occur. That means that it essentially looks like representations of the fundamental group on the open strata with compatibility conditions when you have intersections. And the definition then of the singularity of the normal function is in the limit, you look at where it lands over here. Well, that's the definition of the singularity of, well, admissible. That always happens in the geometric case. That's where the singularities are defined. They're defined as a section of a constructible sheet over the boundary divisor over which the singular fibers occur. What's interesting is that in codimension 1, there are no singularities. So the singularity of a normal function, unlike most types of singularities you think of, an analytic function or whatever, these only occur in codimension at least 2. So in codimension 1, these limiting intermediate Jacobians, or even in the case of algebraic curves, the limits of the Jacobians are called Nero models. It's what happens to the Jacobian of a curve when the curve becomes singular. And what you get is connected abelian variety fitting in an exact sequence whose quotient is a finite group. It's the group of, it comes from the group of components that you get in the limit. Okay. This has a continuous part and a discrete part, and this is just repeating what I said a minute ago. In the geometric case, in the limit, you end up in subquotients of these Chow groups. So just a baby example of what's going on. Take a family of algebraic curves, and suppose you have a divisor. Say these are plus and these are minus. So it's 2 points minus 2 points. And you go to the limit. Okay. And suppose in the limit on the normalization, this divisor is the divisor of a function. So that means that in the limit, the continuous part is 0. And so you get a well-defined neuromorphic function in the limit with zeros here, poles here, defined up to a constant, and their quotient at the 2 points lying over the double point is an element in K1 of C. So this is the sort of flavor of what you pick up when you degenerate the family of varieties and you end up in higher orbital Jacobi maps, cranking out arithmetic stuff. A more interesting example, classic example from the physicists, is this one, the quintic. And in the limit, this is the connected components of the limit of the intermediate Jacobian. Jacobian of a quintic curve, bunch of copies of that, bunch of C stars. And there's further cycles giving a something non-trivial in this quotient group. And it gives you, in fact, a map from Chow 2 of C mod 3 to C Z2. So that's again how something very concrete, taking the orbital Jacobi map of a family of, in this case, a difference of lines on a quintic going into the limit, you end up with arithmetic self. I think I'll skip this. This is just another example. So this is the sort of mechanics behind getting at the singularity of the normal function. You have to try to split exact sequences of mixed Hodge structures. And you split them in 2 different ways. One is you split them over Q, and the other is you split them preserving the Hodge filtration, and you take the difference. That's the extension class. You split over Q, you have monodromy. And the interesting thing geometrically is that the monodromy of the normal function, what does that mean geometrically? You have say in the case of algebraic curves, you have a 1 chain whose boundary is a 0 cycle, a bunch of points. Now let everything become singular. In the limit, you're going to get a 1 chain of some kind. the theorem is, non-trivial theorem, is that it's actually a vanishing cycle, so-called vanishing cycle in the sense of singularity theory, and the local invariant cycle theorem tells you have a relation like this. The monodromy of the normal function is related to the monodromy of the smooth curves over Q. That's in effect saying that the singularity of the normal function, when you have only one parameter over Q, is zero. It's a torsion singularity. When you have several parameters, you degenerate along each direction. But the thing you have to do to split the sequence, because it's torsion, you can add something to split it, depends on which direction. And the result then is that you get a Cazul type complex. And the singularity of the normal function is in the first homology of this gadget here. So this is a thing that you get by looking at monodromy of the normal function. So you have a cycle that's the boundary of a chain, go around the singularity, bring it back. The thing that it's bounding doesn't change when you go around. So that means that the thing, when you go around, the boundary is a cycle which comes from the homology of the non-singular part, if you like. You do something involved in the mechanism of how the Hodge structure varies, the Gauss-Bonnet connection and all of that, and that leads you to the singularity of the infinitesimal invariant and a different Cazul type object, something involving Hodge structures, not just geometric, not just monodromy. And the punchline then is that monodromy minus the identity and the log of monodromy differ by something invertible, which gives a quasi-isomorphism between these two Cazul complexes, and under the induced maps, the singularities line up. So the singularity has both a Q structure, a geometric structure arising from monodromy, and a Hodge structure arising from the limit of the infinitesimal invariant. And in the limit, those line up. That's the geometric content of the theorem. I will skip this. I would make one remark that when Hodge structures degenerate, the basic tool that's used to analyze the degeneration is what's called the nilpotent orbit theorem of Schmidt. What that says is that the degeneration of the Hodge structure is approximated by something arising, if you like, from Lie theory. It's a nilpotent orbit on a homogeneous space. In classical terms, when you expand periods, there are polynomials and logarithms with holomorphic coefficients. You know, you look at any old textbook on ODEs, that's what you see. The nilpotent orbit kicks out the log part, the singular part. It freezes the holomorphic coefficients at the origin and kicks out the log part. So that's in one parameter. Schmidt's nilpotent theorem, orbit theorem is one parameter. Because you have no singularities of a normal function in codimension 1, you're going to have to go to codimension 2 to get anything like a nilpotent orbit theorem. So the technical part of this theorem is to extend the Schmidt nilpotent orbit theorem to several parameters where you have not just one nilpotent orbit, but you have a complicated family of nilpotent orbits depending on a finite number of discrete quantities. And so it's not a multi-parameter in the usual sense, but it depends on geometrically the singularities go out in codimension 2, but the way they go out in codimension 2, the two different ways may not match up. There may be some way of correcting things that works this way, but not that way. And in that mechanism, you end up constructing for the normal function and approximating nilpotent orbit, but it only gives information in codimension 2. In the last few minutes, I want to talk a little bit about some of the outstanding issues of algebraic curves, algebraic cycles on algebraic varieties. The central one is the conjecture of Bloch-Beilinson. And just to briefly explain these involve arithmetic Hodge-Jacobi maps, somewhat different than the ones I did before. So let me just illustrate for the case of an algebraic surface. Codimension 1 cycles, those are curves on the surface, there's just the curve variety. Codimension 2, there's 0 cycles, and here the mystery begins. This is where the mysteries begin. Go back to Mumford, he said that if the algebraic surface has non-trivial homomorphic 2 forms, PG is non-zero, then the dimension of the kernel of the Hodge-Jacobi is infinite. Right? So you miss an infinite amount of stuff in the child group. And this is just a sketch of how he proved it. It's a symplectic argument. And that led people to conjecture that if you have a surface that has no PG, has no holomorphic 2 forms, then the dimension of the child group is finite. That it's the holomorphic 2 forms somehow interacting with the points on the surface that creates this infinite dimensional object. And Bloch and collaborators checked this by it was a lengthy exercise using the complete classification of surfaces. You just go down the list of all the different types of algebraic surfaces. Many of them you can check off fairly easily. The hard one is the Enrique surface, which is frequently the case. That's the most interesting surface in a lot of ways. As an example of the sort of thing that's not known, just take a projective plane defined over Q, right? And take a smooth curve of degree 6 defined over Q. And even degree, you can take a 2-sheeted branch cover. And that's an algebraic surface that has, it's a Kummer surface, PG is 1, defined over Q. And look at a point on the curve of a rational point on the branch curve. Okay. I'm sorry, that should not be C of Q. Look at a point on P2 and look at the 2 points lying over it. That's a point on P2, not on the branch curve. So you have 2 points lying over it. Downstairs, you have a point defined over Q. It's not known if the difference of those points is rationally equivalent to 0. The sort of simplest, if you like, hyperelliptic type algebraic surface you can think of. You ask the simplest question about when a couple points, a pair of points, are rationally equivalent to 0, and the answer is not known. The Bloch-Beilinson conjecture says that there exists a filtration on the child groups for which there are Hodge-Jacobi maps on the graded quotients. The first 2, the 0th one is just the usual cycle map. Just take its homology class of an algebraic cycle. If that's 0, then you go to the Hodge-Jacobi map. That's the first invariant. Suppose that's 0, then what happens? And that's where the mystery lies. So how are you going to construct candidates for these higher Hodge-Jacobi maps in this sense? There's a construction that's been given, but it depends on the block type conjecture that was mentioned earlier, and depends on the generalized Hodge conjecture as formulated by Grothendieck and others. If you take any field with characteristics of 0, then you can make an algebraic object geometric by looking at what's called the spread. So the field is a finite extension of a purely transcendental field with some relations here. And you have the spread just given by taking these as the equations. So it's a way of starting with a variety defined over a small field, K, even a number field. And if you have a cycle load that's not defined over the number fields, defined over a much larger field, you can spread the cycle and try to study the geometry of what happens when you do that operation. So that's an arithmetic type construction. So this is the spread construction, and this is what I mentioned before. The first case where you get something non-classical is a regular surface defined over Q. You have the spread, you have a 0 cycles, that's a bunch of points, but they may not be defined over Q. You have the spread, and these points, since it's a 0 cycle, when you spread them, it remains a 0 cycle of degree 0, so it's the boundary of a 1 chain, and the 0 cycle is the boundary of 1 chain, and as you traverse a path in the first homology of the spread space, this is an arithmetic or algebraic type construction, you get from that construction, you'll get a 2-dimensional object. It's the union of 1-dimensional objects, taking away some ambiguity. And you can integrate holomorphic 2 forms over this 2-dimensional object. That's the sort of thing that appears in conjecturally the constructions for the Bloch-Valence invariant. I think I will not do this. I think to close, I'll go back to the case of the quintic. So this was mentioned earlier. You have disjoint lines, these are the normal bundle, the infinitesimal invariant, and it was been known conjecturally, it was known classically that the infinitesimal invariant is generically non-zero. And that's a nice statement, but if you're a geometer, you say, fine, that's a generic object. But suppose you give me a specific quintic and a specific pair of lines, then is the thing non-zero? Now that has only recently been proved to be the case. So quintic is non-singular for a pair of disjoint lines. This is non-zero. I think the result is, it's not a great theorem, but the interest is that you're getting at something specific, not generic. And that's what I see a lot of the issues involving the infinitesimal invariant normal function and related things as being set as having an important component to do things specifically, not just generically. And I think these are the references from these papers. I think everything that I've said here is, except for that last little part, is contained in these papers. They're reasonably good expository papers, and I think that the subject is one that has developed a lot of things which are fairly interesting and concrete geometric questions, some along the lines that I've mentioned, are yet to have any way to get at them. Thank you.